Hello dear students, here we'll discuss some of the examples regarding the topics that we have covered till now. So the first example is based on a solved example from the textbook of Fluid Mechanics and Hydraulic Machines by R.K. Rajput. So the example goes like this. In a fluid, the velocity field is given by V equals 3x plus 2y into I, that is a unit vector in x direction, then 2z plus 3x square j plus 2t minus 3z k. The question is, determine the velocity components u, v, w at any point in the flow field, then the speed at point 111 and the speed at time 2 seconds at point 002. And it also asks to classify the velocity field as steady or unsteady, uniform or non-uniform, and 1, 2, or 3 dimensional. So the last part we can answer right away. That is, since v is given at x, y, z, and it depends on t. If you look at the expression of velocity, it has the t term here. That means which time the velocity will change. If you put t equal to 1, whatever is the velocity, if you put t equal to 2, then the velocity will be different. That means quite clearly it is an unsteady flow. Similarly, whether it is uniform or non-uniform, since it is a function of space dimension, x, y, or z, whatever it is, that means if you put different values of x, then you will get different velocities, or different values of y or z, and it will give you different values of velocity. That means the flow is non-uniform. It changes with space. And whether it is 1, 2, or 3 dimensional, because it's a function of both all x, y, and z dimensions, that means it is a 3-dimensional flow. Now, let's come to the first part, that is the velocity components u, v, and w. In this problem, the answer is actually quite clear, because the expression is given in such a way that this is obviously the x component of velocity, that is 3x plus 2y is equal to u. Then the y component v is equal to 2z plus 3x square, and the z component w is equal to 2t minus 3z. As you can see in the solution, these are u, v, and w. Now it asks the speed at point 111. It's asking speed because that means it is not asking for the direction, it's only asking about the magnitude of velocity, which is called the speed. So you simply put the values of x, y, and z as 111 in the expression. So you get u equal to 5, v equal to 5, and w equal to 2t minus 3. Here t is remaining as t because the value of t is not specified. Therefore, we are keeping it as t. And the resultant speed will be, for 3 mutually perpendicular vectors, the resultant is square root of their summation squared. So their summation squared is u square plus v square plus w square, and 5 square plus 5 square plus this. So you'll get this kind of an expression. So this is the speed at point 111. Now, the final part is speed at t equal to 2 seconds at point 002. That means x equals 0, y equals 0, and z equal to 2 at time equal to 2 seconds. So similarly, you just put t equal to 2, x equals 0, and y equal to 0, and z equal to 2. And putting all those things wherever applicable, you get the velocity magnitude or the speed as 4.472 units. See, here we have written units because the actual units of x, y, z, and t are not specified. Now, let's take this problem a little bit further. What if we want to find the acceleration of this flow field? Now, from our earlier discussions, we know how to find out the acceleration. Acceleration in x direction is du by dt which is the total derivative or material derivative, which is given by summation of all these terms. Del u by del t is partial derivative of the velocity with respect to time only. Then all these are partial, this is called the convective acceleration, while this was the local acceleration. So this gives us the acceleration value. Similarly, in y direction, we can write the acceleration as this one, and in z direction, a z equals dw by dt, and it will appear like this. Now the only thing that we need to do is put the values of the expressions for u, v and w as applicable, and we'll get this kind of an expression where del u by del t is del t of 3x plus 2y. 3x plus 2y is u. Similarly, u del u by del x plus v del u by del y plus w del u by del z. And when you perform the differentiation, you'll get the first term is 0, second term is this much, and so on. So finally, you'll be arriving at an expression like this. Similarly, if we try to find out the accelerations in y direction, then we'll get an expression like this, and in z direction, we'll get an expression like this. Now, if I ask you what is the acceleration at a point 24t at a moment where time is equal to 2.5, it may be second or minutes or hours, whatever. So what you just need to do is put the values of x, y and z in the expressions that we have already determined, and find the values of ax, ay and az, and the final magnitude of acceleration at that point resultant will be root over the sum of the squares of the components. So this part you can do yourself. Now in this problem, the flow field was already given to us in the form of this expression of v equal to u into u is given by something, v is given by something, and so on. But practically, how did they arrive at that expression? That we do not know yet. But if we start from a simple problem, we can actually find out how to arrive at that kind of an expression for velocity. That is, how to find out the velocity field. The velocity field, in a sense, is just the expression, mathematical expression, by which you can explain what will be the velocity at different points in space at different moments of time. So let us define a flow field, and we'll take a simple example of a pipe. So this pipe is having a length L, total length L, and its diameter is changing, is reducing, decreasing in this direction. And at the beginning of the pipe, the diameter is d1 and the velocity is u1, and at the end of the pipe, the diameter is d2 and velocity is u2. Now, for simplicity, let us consider steady and incompressible flow. If it is steady and incompressible flow, that means u1 at this point is not changing, and u2 again is not changing. The geometry is obviously fixed, and since it is incompressible, so we can write the continuity equation like this: u1a1 equals u2a2. Velocity into area equal to velocity into area. Now, to define the flow field, what we need to do is find an expression for velocity at an arbitrary coordinate x. That is, if you consider any cross section at a distance x from the beginning of the pipe, suppose. Beginning means, in this case, if you consider a coordinate reference system, this is the origin where x equals 0. As we move on in this direction, x increases. At this point, x equals L. In this particular problem, we are ignoring the velocity variation as well as the velocity components in y and z directions, so we can fairly treat it as a one-dimensional flow. There will be some component in the y and z directions, because you see the flow lines are a little bit inclined. But for this problem, we are going to ignore them. One additional information I can put it in here, that is, you see these dotted lines. These dotted lines are the stream lines. So at any point, they are tangential to the velocity. And as the stream lines become closely spaced, it means that the velocity is increasing. At this point, they are widely spaced. That means the velocity is small. At this point, since velocity is larger, the streamlines are becoming closer and closer. Okay, now we'll put that picture here. To start finding out the velocity field, we need some reference information. So that information in this case will be the information about continuity of the flow. That is the continuity equation. So this is where we can start the solution of the problem. U1A1 equals U2A2. Now, instead of the section 2, that is the end section, we can take any other section in between here. That is at a distance x from the beginning. If that is the case, we can write the continuity equation like this also. U1A1 equals UXAX, where UX is velocity at this cross section and AX is the area of this cross section. Why have we done that? Because ultimately our goal is to find an expression for UX. You see, the UX is the velocity at any arbitrary location x. That means if we can formulate this kind of an expression, ultimately we need to find an expression for ux. That means we will take ux to the left hand side and we'll put all the other things to the right hand side. So let's expand this whole thing, because a1, ax, these things are right now unknown. We'll write a1 equal to pi d1 square by 4, that is the area of the circular cross section. Similarly, ax is pi dx square by 4. And pi and 4 can be cancelled, so it remains u1 d1 square, ux dx square. Now, this dx quantity, it's still an unknown. Dx is the diameter of the pipe at this location. And it seems like this is a function of x also. So instead of dx, we can write it in terms of x rather than keeping it as an unknown dx. So can we do that? For that, we'll consider the geometry of the pipe. So over a length of L, from here to here, the diameter changes by d1 minus d2. That means here the diameter was d1, here it is d2. So over a length of L, if it is changing linearly, suppose, the change is d1 minus d2, or the reduction is d1 minus d2. So if you consider a unit length, over a unit length, it will change by d1 minus d2 divided by L, right? And over a length of x, therefore it will be d1 minus d2 divided by L multiplied by x. That means at any distance x, here the diameter will be given by dx equals d1, the original diameter here, minus whatever is the change over a distance x, which is this quantity. So d1 minus d2 by x into L, or d1 minus d2 divided by L multiplied by x. Okay, so we have found out an expression for dx. Now we'll just put this dx in this expression. So this expression now becomes u1 d1 square equal to ux multiplied by this whole term squared. So from this, just take ux to the left hand side and you have an expression for ux in terms of some known quantities. U1, D1, D2 and L. So this is how we find out the flow field. This is a very simplified example involving only one dimension, and we have already assumed the flow to be incompressible and steady. So we are also finding out a very simplified expression for the flow field in x direction. Now here I would like to introduce you to something called a boundary condition. You see, all these quantities, I have told you that these are known quantities, but in reality they have to be known. And if D1, D2 and U1, those things are known, that is the diameter at this point, and the velocity at this point. If these things are known, then we can find out this ux at any point. Instead of u1, if u2 was also known, then also we could find out a similar expression. That means u1 is the boundary condition. That is the velocity at this cross section, the end cross section, in this case the beginning cross section, is the boundary condition. If that is known, then we can proceed with the problem, and instead of dealing with an expression, we can actually assign some numerical values there. Now I'll leave you some problems to solve at your home. So the example that we have discussed previously, that is this example, where the flow field is given by this, we'll give some numerical values. That is L equals 50 centimeter, D1 equal to 8 centimeter, D2 equal to 3 centimeter, and U1 equal to 1.2 meter per second. So you just need to find out the velocity and acceleration at x equal to 25 centimeter. So that you can do simply by putting the numerical values and find out some numerical answer for the problem. Another problem I'd like you to solve, that is this one. For a 20 meter long pipe of rectangular cross section carrying water, determine the flow field if the width of the cross section at the beginning of the pipe is 30 centimeter and at the end the width is 10 centimeter. So it will be this kind of a cross section instead of the previous problem, which was a circular pipe. In this case it's a rectangular pipe. So at this point, this cross section, the width is 30 centimeter and it is reduced to 10 centimeter when the pipe is ending. The total length of the pipe is 20 meters and the height of the cross section, that is whatever is the height here, the same will be the height here, and the velocity at the beginning is given as 1 meter per second and the height of the pipe will be given as 40 centimeter per second. 40 centimeters. So try to find a similar expression for this pipe. That is, you need to find out the velocity at any distance x starting from the beginning cross section and find an expression for ux. So that's all for this one. Thank you.